All right, another example of 80s awesomeness. 80s HP15Cs. I'm sticking with HP15Cs for a while. So here's the math problem we're going to solve. Let's actually go here first. So imagine you got two formulas here, two functions. Y equals x squared plus 1, which is the blue one here, and then y equals square root of x, which is the red one. The question is, what is the minimum distance between these two? Like, how close do they come? What's the minimum line length that you could draw between any 2 points on these curves? All right, so how close do they come? Now, the first thing you'll notice is it's not necessarily going to be on a certain x value, like straight up and down. All right, so you can't assume that. It's going to be, in this case, sort of curved in this direction. Okay? Now, mathematically, you could, I think, it's going to be, basically, you're going to take the derivative of these functions, which gives you the slope of the tangent line at any given point. And the first thing you're going to notice is that the shortest distance is going to lie between two parallel tangent lines in between these curves, okay? And it's going to be normal to those two. It'll be at a right angle to both of those parallel lines. So, it's going to be somewhere, if I can get a pencil. So it's probably going to be, somewhere around, let's say there and there, kind of like that. And at that point, what's going to happen is, and I'm sure you could prove this mathematically, but at the tangent lines at those 2 points, well, first of all, they'll be parallel, and they'll be normal there. But that's just the mathematical way of going about it. But what I figured I'd do is write a recursive kind of program on the HP15C to estimate this, to kind of get me, in other words, what it's going to find is an upper bound to this value. Like this, what it's going to spit out is a number that is maybe close to the actual value, but it won't be perfect because I'm not mathematically solving it, but it's going to give me an upper bound. So I'll know that it won't be this distance, the true minimum is no larger than whatever this thing spits out. So here's the algorithm that I've decided to go with. What I'm going to do is, in a certain range, between here and here, I'm going to have the calculator run through and kind of randomly sample lines between 2 points along this thing and keep track of the shortest one and just spit that out. So as you can imagine, like, let's say we choose this point and that point. There's the line, here's the distance. And then choose this one and that one. There's a line, find the distance. Is it lower than the prior minimum? If so, save that as the new minimum. Do another one. So what I'm doing is every time I'm taking random points along the line in between here and here, finding the distance between the points, comparing it to a running minimum that I have, and just doing that a bunch of times, and then when it's done, it'll spit out what the minimum is that it has. So it's going to kind of be in the ballpark. See, what it's doing is randomly sampling all kinds of lines in between, here and here along these functions. Okay, so here's kind of the way it looks. I've already talked about that. You got the function. A couple things here. You're going to have you're going to use the random function of the HP calculator to give you a random number between 0 and 1. Multiply that by the distance in your interval here, and then add that to the starting point to tell you like how far to go. But it's going to be random in between here and there. So that gives you the x, and then you plug in the y for it for F1, and then you do it again, another x, the y for it for F2, and then you do, you got 2 points, A and F1A, B and F2B, and then, it's basically A squared plus B squared equals C squared, so you can, that's the math to figure out that distance, okay? So we're going to be doing that. Here's kind of the pseudo code that I wrote to start with. But it's just the iteration of stepping through, randomly choosing the x's, calculating the distance, keeping track of whether that's lower than the current running minimum that you have, and then just doing that for a certain amount of time. There's the program there. Starts here. It's E. This is inserted here. Storing the A and B here, and then I'm starting with a huge number, storing that in my 0.7 storage register, which is my running minimum. Okay, and then there's where I'm choosing the random X. This is for function 1, and then I store that, repeat it, do it for function 2, and then I've just hard-coded in the formulas here for these two functions, x squared plus 1 and then the square root of x. And then it calculates the distance between those 2 points, and then test 8 is x less than y. So what I'm doing is recalling the running minimum, this huge number at first, comparing the distance that's currently been calculated on my 2 random points I just chose. If it's less than, then I store it as the new 0.7, otherwise not. And then ISG is increment and skip if greater than, and I've got that counter in 0.5. Okay, and then the format of that thing is your starting number dot how far you want to go in 3 digits. You know, if you want to do like 50 iterations, and then what increment you want to increment in 1. So that just tells it run this thing 50 times in increments of 1. You could do 100, you could do 999. I've done it. It takes a long time on the 15C. And then you enter the min, the max, and then run it. That's kind of the format. So you have to pre-fill this thing in 0.5. So let's do that. So we're going to start it over here. So we're going to put in 0.5, 0, dot. Let's only do like 10 because this takes a while. 0, 1, 0 in increments of 1, store 0.5. Now I know if I look at this thing, it's between like 0.25 and 0.75 is where it happens. So let's limit it to that. 0.25, enter, 0.75, go sub E. All right. Again, this is going to give me an upper bound for that distance. So it won't be exact, but I'll know that the minimum distance between these 2 points in that range is no greater than whatever it found. And you can get more accurate by running this more times and by shortening that little range, 0.25 to 0.75, as you start to zero in on where you know that minimum is. Okay? So let's just see what we get here. I don't think I've actually ever run it with only 10. So I'm not sure what I'll get. I've run it with like 25 or 50. So 0.5358. So you know that the distance between those two is less than 0.5358. It's somewhere in that range, but it's definitely not greater than that. Okay? So just another example of the coolness of that old calculator and how it's pretty simple. That ISG, the random number, the test functionality to compare it with the prior number, and that's pretty cool. So maybe I'll go to Wolfram Alpha and actually find out the real distance between the two and compare this. But anyway, long live HP calculators. The math is smarter than the both of us.